All right, we're back for another coding session. This time, I want to expand on our expressions. I would like that we can do more than one math operation at once. So I've gone down a bit of a rabbit hole with this. I've done a bit of investigation. And there's two main ways that I can see to do this. The first, we've got an example grammar here. This, I think I prefer this grammar notation actually. I think at some point we're going to switch to something more like this. We have nice pretty arrows instead of these ugly looking things, but the rest of it I prefer to what we have, so we'll get there at some point. But anyway, this grammar here is basically saying, you know, an expression is an equality expression. An equality expression is an additive expression, and then optionally it can have equals or not equals and an additive expression, and you can repeat this pattern. And then we have the same thing where we have two multiplicative expressions, you know, and we can repeat this. So we've got sort of like one set of operators with a certain precedence in one production, and that's constructed from operations with an operator that has a higher precedence, and then that's constructed from operations with an even higher precedence, and then that's constructed from what they call primaries, which is like your base elements in the expression. And so what this does is basically it means that our grammar is defined in such a way that if we do recursive descent parsing on this grammar, we should end up with a structure that evaluates the expression correctly, you know, handles the precedence correctly. So that's one way to do it. We're talking about precedence climbing in this section, which is another method. So here they're saying, you know, this can require 5 function calls just to reach a primary. So it's not the most efficient. I did actually have a crack at this, and it ended up, because I like the idea of just having the grammar like this, and then when we reflect the grammar in our AST, it just works. But yeah, it ended up being more complicated than I thought. Then I actually also had a crack at this one. This here is the actual precedence climbing algorithm in pseudocode. So this is a different way to achieve it, and we'll visualize that in a second. So I spent 2 hours on this one, implementing this one and recording it for you guys. Or I thought I was recording it until I got to the very end after 2 hours and went to stop recording, only to find out that I had not started. So this is take 3. Because first I tried this, then I tried this, and now, fingers crossed, we're actually going to get a result. So let's first go back to our grammar and update that, because it's quite a easy update. You know, all it really is this. So we can, on the right-hand side, have another expression, which means that it could be, you know, another add or another whatever it is, or it could just be a term or a primary, as they called it. Maybe we'll take their terminology actually. Primary, because I did do a bit of investigation into this, and I think term is kind of specifically for an additive operation, so a plus or a minus. These would be, on either side of these would be terms, either side of these are factors. And yeah, in that grammar we just saw they used primary, so I'm just going to go with primary because I feel like it's a more general thing. So here's our new grammar. Now, we're going to attempt to do this with the precedence climbing, and we're going to try and visualize this. So maybe what I'll do is I'll bring this out over here, and over here we will have our algorithm. Okay, we're going to make a tree. So let's say if we go back to our code, this is what we have at the moment. So let's say we change this to something more like this, a more advanced expression. This means that these two on the sides need to be evaluated first, and then the plus gets evaluated. So let's try this. If we just put this in here and make it a bit bigger. Okay, I don't really want it to be super long. That's a little unnecessary. Just a bit bigger. Okay. And then we'll steal one of these boxes. All right. So this algorithm goes that once we go into parse expression, the first thing we do is we parse primary. And remember, primary is just like the leaf nodes, or it's just our individual integers or variables. So parsing primary gives us a y. Great. And we set minimum precedence to 0 and we step in. So actually, let's try to put, so this is our left-hand side is this one, and this is going to be our right-hand side. So we've got a left-hand side, a right-hand side, and then maybe the look ahead we'll put over here. I just want to kind of keep track of everything. It's kind of a complicated algorithm, so let's see how we go. So our look ahead is peeking the next token. The next token is the divide. Okay. While look ahead is a binary operator whose precedence is greater than or equal to the minimum precedence. So for precedence, so different operators have different precedence. I think we had it open, last time I tried this, we had it open here. Here we go, operator precedence. So these are the Odin operator precedences. For the purpose of this run through, we'll use theirs. So a divide up here has a precedence of 7. So 7 is greater than or equal to our minimum of 0. So, and it's a binary operator. So operator equals look ahead. And I guess the operator should kind of go up here. You know, it's between the left and the right hand side. So that's always also a slash. Now we advance to the next token. So we've consumed this operator. And then we set the right hand side to parse primary. So parse, that's a 7. If we parse the next thing. So that's our right hand side. Now look ahead is picking the next token. The next token is a plus. Put that in there. On our look ahead. And now we say, while look ahead is a binary operator whose precedence is greater than op. There's also this mention of right associative operators. We're going to ignore that for now because we don't have any. We just have these basic math ones, which are, I believe they are left associative, or yeah, I don't know. I know that they're not right associative, so we don't need to worry about that. So let's see. Look ahead is a binary operator, and precedence is greater than op. Well, what is the precedence of plus? It's 6. Maybe we can put our precedences with our operators just to make it a bit clearer. We call it a prec. So they're just not, okay. That's a 6. So the look ahead precedence is greater than ops. That's not true. It's lower. So we're not going into this while loop. So let's skip that. And then we end up here. And it says left-hand side is the result of applying op with operands LHS and RHS. So we might have to expand this guy a bit. So this becomes, this is why I put like a box around it, because I knew it was going to get bigger. This becomes, well, okay, so let's keep that there because we haven't changed what RHS is. So we'll just say RHS is that. Basically, we're updating LHS. That's what this line is doing, right? So LHS becomes this. Okay? Great. Then we go back to the top of the loop and we say, look ahead is a binary operator whose precedence is greater than or equal to the min precedence. Well, 6 is greater than or equal to our min precedence, which is 0. So we go in and we say op equals look ahead. So this goes up here. Then we advance to the next token. So that's basically consuming what we had peaked. You know, we consume the plus. And then RHS becomes parse primary, which is our 3. So that's a 3. I think actually in this algorithm, RHS is always going to be just a single thing, but let's just keep the big box anyway. So now look ahead becomes picking the next token. The next token is a star or an asterisk, which also has precedence 7. We can confirm over here. Star is 7. Sorry, it's probably quite small. Okay. So that was this line. Now, while look ahead is a binary operator whose precedence is greater than op. That is true this time. It's a binary operator and its precedence is greater than op. So we go into this loop and we say RHS becomes the result of calling, we're going to recurse here, calling parse expression 1. So I think how I'm going to represent this is we're going to, let's make even a bigger rectangle. Duplicate that and put that down there. So this is our first call. This is our, we're recursing into the next call, and that's down here. So that's going to represent that. So, and we're going to call it, so actually let's shift, that's right. Put these boxes in here because it needs a left and a right hand side. And we're passing in RHS to the left hand side. So that becomes there. And the minimum precedence maybe we need to visualize that as well. I hate how this box keeps coming up. I don't have enough space for you, box. Go away. So min prec is 0. and what is it going to be over here? So it's the precedence of op, precedence being 6, plus 1 if look-ahead precedence is greater. Look-ahead precedence is greater, so it's plus 1. Otherwise, it's 0. So 6 plus 1. Like so. Sorry it's so small. And also I'm in the way, aren't I? So I'll try to zoom in a bit. But you might just have to try and watch this on a big screen for this part. It's kind of a lot of information to take in at once. Okay. So yeah, those are the things we defined. So now let's step into that. So we've got our LHS and I'm in precedence. Now look ahead is picking the next token, which is the star. Because we did already, previously we did look ahead this, but we never consumed it. So look ahead is still the same thing. Okay. Now, look ahead is a binary operator whose precedence is greater than or equal to minimum precedence. It is a binary operator, and the precedence 7, 7, it is greater than or equal to. Great. Op becomes look ahead. Done. Advance to the next token, so we consume the asterisk. Right-hand side becomes parse primary, which is another 3. This is 3 on the end. Great. Then we look ahead and pick the next token. There is no next token. So it's like end of file in this case. It could be something else that's not a binary operator if we had like more lines of code. But in our case, we're just going to say end of file. Then we're going to say, while look ahead is a binary operator, well, that's already false. That's not a binary operator, so we're not going into this loop. So we go here, say LHS becomes, just to make it clearer, we're copying this one and bringing it over here. We copy this one and bringing it over to here, because LHS becomes the result of applying op with operands LHS and RHS. So it's bringing all these things together. There we go. Done. Then we go to up to this while loop and we say while look ahead is a binary operator, that's already false. So now we come down to the bottom and we return LHS. Okay. So the result of all of this is LHS. It's this one here. So let's go back up to this one here, this call. And so we just performed this. So now the next line is look ahead equals pick next token. So now this is also EOF. And then we go to the top of our loop, not a binary operator. So then we go here. Sorry. Before we do this, we need to do this assignment. So RHS, so let's back up a step. So RHS becomes the result of this. And it was LHS is what got returned. So this is coming up here to replace that. Okay. Now we go to the next line and change our look ahead, and it becomes EOF. And we come to the top of the loop, not a binary operator. So now we come to here, LHS becomes the result of combining them. So basically, we don't have enough space, so let's just arrow. Basically, we're going to end up with this, right? Now, all of this is LHS. Okay, now we go to the top of this loop. Look ahead as a binary operator. Nope. So then we return LHS. And then we return from this one as well. So remember, this whole thing was LHS. So this is our result. Okay, so in order to evaluate the add, we're first going to have to evaluate this divide and this multiply, and then we can evaluate the add. Great, so that's what our algorithm gets us. Okay, that's enough of that. Let's bring this over. What I might do is just take all of this and move it a bit further away. Cool. And yeah, you can come in and have a look at this. It's in the description if you want to have a look at all this stuff. So now let's implement this pseudocode. So our parse expression is going to become these two functions. Okay. We don't need any new tokens. We're not adding tokens. So we go parse expression. Let's go like this, and it's just going to be return parse expression 1. We'll just use the same naming as them. So that's _1. And we need to pass the primary in. Parse primary. And this is going to become parse primary down here because we call it a primary now. Failed to parse primary. Okay. So here we go. This is the left-hand side. That's coming in. So we also need a left-hand side and a min precedence. Min precedence int equals 0. So we have a default of 0. So we don't need to specify 0 here. Okay. Let's be explicit. Let's be explicit. So now in here is where we want to. Let me have a look at what nodes we have. Do we have an expression node? No, we don't. We have an add, subtract, multiply, divide. Okay, great. So I think we're just going to cut all this out for now. And then we're going to throw this pseudocode in here. And it's going to create a big mess for now, but that's all right. And because we need to assign to LHS, see here, and return this new LHS, I'm going to create a final LHS because in Odin, parameters are immutable. I can't reassign this. So I'm just going to create this final LHS variable, which is something that I can reassign. And then anywhere that uses that variable, which is these two places. And we just have to be careful that anywhere in here where we're referencing an LHS, we actually reference final LHS. A left-hand side, I should say. Okay, so look ahead equals peak token. Easy enough. And for look ahead is binary operator whose precedence is. So I think for these, we're just going to make a couple of utility functions. Is binary operator and we're going to pass in our token and get back a Boolean. It's going to be kind of like something like this, you know. Maybe I'm going to comment out this stuff for now because it's causing all sorts of havoc with my editor. So it should be more like that. Okay. So if we didn't find anything, then it's like, no, there's no failure. The default case is false if it was not a binary operator. So if the token type was plus, minus, going to return true. Actually, maybe what I would do here, multiply, no, not multiply. We're talking about tokens here. So it's asterisk and backslash. Okay, so those are our 4 possible tokens that would be a binary operator right now. And I'm going to add this fall through keyword. So one of the things I like, I've mentioned this before, but one of the things I like about switch statements in Odin is they do not fall through by default. You have to explicitly fall through to the next case. And you know what? I'm not going to do it. I mean, it's the same amount of code. So let's just do that. So those are binary operators. And then the other thing we wanted to check is the precedence. So binary operator precedence. And we'll return an int. So for a plus, we're going to say it's precedence of 1, 2, 2. And here is where we want to have error handling. Because if we're trying to get the precedence of something that's not a binary operator, I think we probably did something wrong. Failed to determine binary operator precedence. Okay, great. So when we go back up here, this is all the body of the loop, I believe, right down to assigning LHS. Yes, it's all within the loop. Great. So look ahead is a binary operator. So is binary operator look ahead. And the precedence is greater than or equal to negative min precedence. So binary operator precedence of look ahead is greater than or equal to min precedence. Nice. Op is look ahead. That's easy. Just not used. Yep. Advance to the next token. So that's next token. So that's just because we've only looked ahead. Op. I mean, we could do this and take this line away. That would be the same. But we're just going to stick to exactly what the pseudocode was for now. RHS is the result of parsing primary. Easy. And then look ahead becomes peak token. So we're overriding our look ahead. Cool, doing well so far. Like I said, we're not going to worry about right associative, so let's take that out. For, whoops, there we go here. Is this look ahead, is that within the loop? Yes, these two statements are inside the loop. Let's comment them out for now. Comment this one out for now. I don't think we're going to use a named return here anymore. Well, I guess we could actually. We could just say that's final LHS. Like that. Okay. So for, okay, look ahead is a binary operator. We've got that here. Whose precedence is greater than ops. Not greater than, equal to, greater than. Greater than the precedence of op. Then we're going to assign to the right-hand side the result of parse expression 1 with the right-hand side. And the precedence of op, and we're optionally going to add 1 to that. Now, this might look a little bit weird at the moment because we've just established that the precedence of look ahead is greater than the precedence of op. And now we're saying if the look ahead precedence is greater than the precedence of op. That's the same thing. The reason that's in there is because of this bit that we removed. So because this is an or, if this evaluated to true, it is possible that the look ahead precedence is not greater. So we could just say precedence of op plus 1 because we always know. But I think because I do not like adding things because we might use it in the future. But we're probably going to get into right associative later. Okay, let's just put a comment. Let's just put a comment. Note, need to recheck pseudocode for min precedence if adding support for right associative operators. And actually, that kind of makes me want to put a comment in here and say, can I link directly to pseudocode? There we go. I wanted a link that has this in it. Cool. So we can link back to where we got this code. Yeah, so we're saying precedence of op plus 1. And that's not happy, probably because I need to pass in the stream. Yep. All right, we're doing pretty well. Yeah, I need to figure something out with that later, I think. Let's just continue. So this is common. Look at equals peak token. And then down here, we're going to assign to final LHS the result of applying op with operands LHS and RHS. So let's create a new LHS, which is an AST. Well, the new LHS is the op, basically. And then we're going to append to the children of LHS, LHS, right? Oh, to children of new age LHS. And we need to refer to final LHS, not just LHS. Oh, too many LHSs. Yeah, result of applying op with operands LHS and RHS. So now we put RHS there also. And we're going to assign final LHS to the result of that. Does that make sense? Apparently not. I mean, the compiler doesn't think it makes sense. New LHS of type token? Oh, of course. Yeah, these are tokens. So I do need to do this. And I need to go, I need like a mapping, right? Like to node type, we'll just call it. We'll pass in the whole token for error handling purposes. So let's copy this one and say to node type. Should we say to AST node type? Let's say to AST node type. So if it's a plus, we want an add. If it's a minus, we want a subtract. If an asterisk, we want a multiply. And a backslash becomes a divide. Failed to find AST node type. Okay. I think that's basically the algorithm implemented. This is where we want to have some metadata. So anytime we parse primary, we are attaching metadata. So all of our primaries have metadata already. It's the operators that don't. So new LHS down here I think that's, we want to get it from op. Is that what we want to do? I think so. So we get some metadata on there. I'm not sure how good this this metadata setup is, but I think we've implemented the algorithm with a few learnings from last time I tried to do it. Like these these functions here, I did that in a different way at first and it was just buggy as hell. So I found it was best just to have a function that we just call at the moment we need it. Because this look ahead, it's getting reassigned all over the place. Yeah, because I was maintaining the result of this as state in this function, and that was just proving to be a foolish way to do it. And we need this new LHS temporary variable because if we played around with final LHS, it would ruin it before we made it one of the children. Okay, I think what we're going to do now is we're not going to generate yet. Instead, we're just going to print out our AST nodes and check that everything is as we expect. Let's do it like this. There we go. So we have a declaration statement. X and 57. Another declaration statement with a Y and an X. Let's skip close to the end. What we want to see, not the exit statement, before the exit statement. Sorry, this is probably a bit hard to follow. I'll slow down once I get to somewhere interesting. There's a divide. Identify a result. Okay, so we have a node with identify a result. And it also has a sibling, which is an add. And the first child of that is a divide. And the first child of the divide is Y. And the second child is 7. Great. This is looking good. And then we finish that one. And then we find another node multiply, which it's a bit hard to follow in here. But I'm pretty sure that this multiplier is another child of the add, which is great. And it has 2 children, well, I hope. It has a child which is an integer literal 3. And it has another child which is an integer literal 3. And then we're closing everything up. And then we get to our exit statement. Okay. And the exit statement has a divide between x and 2. I think everything looks good. First try. I never did this before. Believe me. Okay, now we go to generate expression. This is going to be interesting. So I think what we need to do is instead of returning a string, we're going to need to pass in. So this part here is really leaning on my learnings from the last time I attempted this. So yeah, I'm not smart enough to think of this up front, but now I know this is a good way to do it, or a way that works at least. So we're going to pass in a register number. And that register number is where we want the result of the expression to go. Now, I did have it open. Let's open it again. x86 64-bit registers. It might be this quick reference that I found it on. No, I remember that was a bit too quick. Here we go. So these are the 64-bit registers. He's put it in this nice table for us. And you can see there's like these named ones. These ones are what we've been using so far. And then there's R8, R9, R10 down to R15. And he's even got R16 down to R31, which he says is with APX. And up here he's got this update where he says there's a new extension for x86-64 called APX, which adds 16 more registers named R16 to R31. And this post was made in 2013. So we can be pretty confident that any computer you come across has up to R31. So the reason I wanted to show this is we have these registers which are just R and then a number. I think R means real, which is a 64-bit number. We don't need to return racks. But what we want to do, instead of putting, so this is the case where we're at a primary, basically. So generate term becomes generate primary. We could actually just, I didn't do this last time, but I think it makes sense that that we basically do this statement within generate primary. So let's do that. Instead of returning a string, we want to pass a register number into here as well. And so instead of returning this address, what we're going to do is I think I haven't got it copied anymore. We're going to generate this, which means that we need the file again. So we're coming from RSP plus something, which I believe is an int. Yes, it's the var offset. But we're moving it into R something. Register num, like that. So we've asked it, we've told generate primary where we want the primary to go. And so we're going to put it into this register R something that we've told it to go. So I'm not really sure what a good way to put these is, but let's just do that. So now instead of this, we have our literal, so we're just going to put our literal directly in there. How to generate primary. I guess that would be else now, because we're not returning in these cases. In these cases. Okay, so we've modified our generate primary so that it's going to put it in one of these R registers. Great. So far sounds good. We don't need to return this. So that line just becomes generate primary. I think we basically just pass everything in. And then we return because we're done. We put the result of the expression into this register number. Happened to be just a single primary, so it was easy. Okay, now down here, we're going to generate primary twice with the LHS node and the RHS node. And the interesting thing is, how do we decide what these register numbers are? We can't make them the same register number, because if we do, then we're going to perform the left-hand side calculation, put the result in, let's say 9. Then we're going to perform this right-hand side calculation and also put the result in 9, therefore overriding the left-hand side. That's the problem we have here, because everything is just linear, right, in assembly. And because we're dealing with pairs, what we're going to do, see if I can remember the math for this, is we're going to say LHS register num is the register num divided by 2 times 2 plus 2. I think that was it. Okay, let's explain what the hell I'm doing here. Register number divided by 2. So let's say we send an 8 in here. That's the lowest number, right? Yeah. Let's say we send an 8 in here. In that case, we divide 8 by 2, we get 4. We times it by 2 again, we go back to 8. And then we add 2, and we get 10. Because we're kind of assuming, when we come into generate expression, we're kind of assuming, oh wait, that's not primary. That's expression. We're kind of assuming that we're coming in as a part of a pair, right? So if we have 8, we're kind of assuming that 8 and 9 are already taken. Those registers are already taken, like, because if this call is this one, so let's just go like this. Maybe that explains. Like we might say, okay, we want to do 8 and 9. So then when we recurse in, we don't want the result of this call to be 8 or 9, because then it will conflict with this. So we make it 10. Okay. So even if this was 9 coming in, then yeah, even if this was 9 coming in, then we're going to do 9 divided by 2, which is 4, because we're doing integer division, times 2 makes it 8 again, plus 2 makes it 10. So RHS, just going to make LHS plus 1 and do something like this. Now, does that really work? You know, honestly, I'm not sure. I'm not sure if that's going to work in all cases. You know, if we recurse deep enough, we might still have issues. Because like I said, when 8 or 9 comes in here, these are going to resolve to the same thing. I guess it comes down to like when we're finished with a certain register and when we're not finished. I think it's probably going to be okay, but we would have to actually look at the assembly of a complex example to see if it's really okay. But this is kind of the approach I'm going for now. We'll make this a default of 8, so that's the lowest R register. It does mean that 9 is never actually going to be used because we're going to skip right past it to 10 and 11 here, and then any other recursive calls are going to go to even higher numbers. So this is put in the left-hand side into racks, which is not really needed anymore. We have the left-hand side register number, so we know the result of this is that our left-hand side is in R, this number. I'm not going to get rid of that completely. I'm going to put it in our divide, because our divide requires the left-hand side to be in racks. Okay. So now we know where our left-hand side and our right-hand side are because we nominated the register numbers and then we generated the expressions. So those would have resulted The results of these expressions are now in these register numbers. So now if we want to do an add, we need to, first of all, we need to put the left-hand side. Yeah, we need to put the left-hand side into this register number, because that's what we've been told where the result needs to go. So we're going to move the left-hand side into here. Let's say assign LHS to result. I'm just going to say assign LHS. Now we're going to do the add, and that's also going to be between two of these registers, these numbered registers. I'm going to do like this because, and when we evaluate one expression, all of the assembly that comes out for a complex expression, I'd kind of like to know this part is the add, this part is the divide, you know. So we assign LHS, then we do it, which would be adding the right-hand side to the output, and we're done. That's it. Subtraction is exactly the same, but we do a sub. And then I believe multiplication is exactly the same, except we do an imul. Division is where things get interesting. Cool. So I'm gonna call it the high dividend high part. I don't know. Because the dividend, or is it the divisor? I don't know my division terminology. When these guys talk about division, they quite often use both the dividend and divisor. So the dividend is the one that's going across to, yeah, so the zero out the dividend high part. So it's dividend divisor. That's the terminology. Dividend is on the left, divisor is on the right. So we zero out dividend high part, which is always RDX. Our AX is where we need to put our left-hand side. So that's one of our numbered registers, the left-hand side. Now the result could be any register is where we want to put our result. And we assign the right-hand side to it. No, this is not our result. It's just the right-hand side, which is what we divide by. Need to put the correct comments. Divide do that, assign RHS, and then we do the actual division. And then because our result now will be in racks, what we need to do is we need to move from racks to register num. Like that. So then we get our result in the correct place. Okay. And I think that's basically it. I think that looks pretty good. We're going to put a default of 8 here. So if when we call it generate expression here, we don't need to pass in, we don't need to say what register number is. We just start at the lowest. So this is going to be a bit different now. We just do that, and then we know that we're talking about R8. I guess now we can put these in an order that I like better. I prefer this order because we're not putting our result in racks. So now we can say generate expression might have used racks. It definitely would have used racks if there was a division somewhere in the expression. But now the result of the expression is in R8. So we don't need to worry about overriding racks anymore. So we can put this in the right order. Very nice. Here we generate an expression using the right-hand side node. Yeah, so those don't even need a printf line there anymore. So here we're assigning to that from R8, because that's our result, right? Yeah. And up here, we can take away the printf line again because we're just going from R8 to the top of the stack. This could be a push. I've mentioned that a few times. We haven't done anything about it. Okay, let's run that. I think we need to actually generate though. We're not generating right now. So if we actually generate, we don't get an infinite loop. I'm so scared of just not seeing this now because we get so many infinite loops. Let's have a look at the assembly, shall we? This assembly looks incorrect. I think what's happened is when I assign a primary, I'm not using printf line. Assign primary printf line. R%. I think I mean R%I. %I for integer. That looks better. So when we declare a variable, we put whatever it is in R8. So this is a bit like we could optimize this, right? I mean, we're just moving stuff around when we don't need to. But then R8 goes to the top of the stack and we move the stack ahead. Here's the same thing, but we started with an address on the stack. And assigning, again, we could have just one move here, but whatever. Here's another assignment. We're declaring. Okay, so this here I would actually like to separate out because this keeps confusing me. So when we generate our scope, just say close scope or something. Yeah, so now it's separate. We know that that's not part of the declaration. So that's just a regular declaration, Here is our massive one, which has issues with the formatting, it looks like. So the assign RHS and the do it. I keep doing that. Sorry about that. You get a flash of white. Oh. Yeah. What the hell? And the assign RHS, I've only put one thing in here. Do I need to do that? Is there anything to do here? Because this could be any register. We know where the right-hand side is. We know it's in this register. I think this is superfluous. These two we need to set up. We need to use these two specific registers for the dividend. But we can divide by any register. We know the right-hand side is in this register. That's all we need. Okay. That looks better. Let's start with the exit though, because it's a simpler one. I also want to... Sorry guys. Sorry for your eyes. I think this is at the top. I just want to put a comment here that says like default exit. There we go. So we know that this is our exit. So we're putting a variable in R10. We're putting a number in R11. Oh yeah. At first I was like, what the hell is going on here? But we assign 0 to the dividend high part. That's correct. Then we assign the left-hand side to the dividend low part. Left-hand side is R10. Good, good. Do the division, we divide by R11, which is the right-hand side. And just to be sure, we've got x divided by 2. So 2 is the right-hand side, R11. We're dividing by it. Good. The result of the division goes into R8. And then we do our syscall, right? Rec60, RDI, R8. That looks perfectly good. So we should, if we run this, and if it compiles, like, okay, looking good. 28, same as we did before the changes. So, so that part is at least working. Now I think I want to put this in here so that we can verify the result of that. But let's look at the assembly first. Okay, so we're assigning a variable and we're assigning 7. So we're doing this. Yeah, then we're doing the divide. So we put 0 into IDX, we put our left-hand side into rex. We've seen this before. Now we divide by the right-hand side, and then we take the result and we put it into R10. Beautiful. Now, so this is what I was talking about before, how we're like reusing these registers, and I thought it might be an issue, but actually, I don't think it is, because we've already put the result in R10, so we don't care about R12 and R13 anymore. So we can happily overwrite them for this multiply. So that's what we do. 3 times 3 is this bit here on the side. So we put the 2 operands into R12, R13. We assign the left-hand side. Yeah, because we want the result to be in R11. So we put the left-hand side into R11, and then we multiply R11 by R13. So the result is in R11. Good. So now we have our results in R10 and R11. And now we do our add. Where we put R10 into R8, and then we add R11 to R8. So now our result is an R8. So we move R8 onto the stack and update the stack. That looks perfect to me. If we run this, it's going to change a bit. Oh no, we already had run it, and the only difference is that like now, so we're taking that variable that we just created and we're assigning it. Interesting. So in the exit call, we have this assignment now, which is, we have quite a few of these just moving things around that are not really needed. I think this is one of them, because we could have just put this maybe directly here. But yeah, we put it into R8, and then we do our syscall with R8 as the exit code. So what are we expecting? Y is 77 divided by 7 is 11, plus 3 times 3, which is 9. 11 plus 9 is 20. That's what we should get. And we get 20. Nice. And if we do times 3, gonna have to get out the old calculator for this one. 3 times 3 times 3 is 27, plus, what did I say, 11? Should be 38. Yeah. I'm just trying to think like what else can we, is there a special case that we need to check for, or, I mean, I'm pretty happy that I'm pretty confident that we implemented the algorithm correctly. Where is the algorithm? Here. And yeah. Oh, this is not the algorithm, this is the generation. But I'm pretty happy that we implemented this correctly. And our generation, I think, is pretty good. The only thing I was a little bit unsure about was our use of the register numbers, but it seems good. So yeah, I think I'm happy with this. I guess one other thing we could test is like if we put a bracket or something stupid in here. Failed to parse statement, invalid token. So the parsing failed. I thought it was going to give us something a little more detailed than that. Like maybe failed to parse expression. I feel like it's within the expression that that's an issue. No? I guess we don't have any failure cases in here, do we? Yeah, it's true. I think this algorithm, this would fail. And so it would have just counted this as the expression. Because it would say, hey, this is not a continuation of an expression. So let's return this as the expression. And then effectively it's like, okay, we're starting a new statement. Because a declaration is just identifier colon equals expression. And we finish the expression. So here's a new statement. And then it's like, well, I can't parse this statement. It starts with a bracket, which doesn't make any sense. Okay. Yeah, I think that's good. We're in an hour 14. And I'm just stoked that we got through this. I'm actually recording this time. That's amazing. And I think we got through it pretty cleanly. I hope it made sense. Yeah, we have some superfluous moving around of stuff that we could optimize, but for the sake of simplicity and not causing bugs and stuff. We're just going to leave it as it is. All right. Thanks for stopping by. Give us a like if you've gotten this far. I guess if you've got this far, you probably do like the video. And yeah, I think that's it. The next one I think we're going to do maybe is expand even further on these expressions, brackets and things like that. Okay. Ciao for now.